See, good afternoon. We are going to discuss about hashing techniques. Okay, so here especially we will be learning um, so yes, we have discussed about partially discussed about hashing already. In this class, we will be having little advanced concept related to hashing. Okay, see, basically, we have studied two searching techniques, right? So, what are the searching techniques we have studied? What are the searching techniques we studied? Huh? We studied two main techniques. One is linear search. Another one is what? Binary search, right? So, the main difference between linear search and binary search are what are the difference between linear search and binary search? What are the main difference between linear search and binary search? Huh? So, linear search we can search the element what's that it can be of in any order, right? So the ordering of the element is not necessary there in linear search, right? So linear search, no need of ordering the elements before, right? No need of ordering. So we will be checking each and every element in the list one by one, right? Suppose if it is a list, then we will be checking each and every element in the list one by one. Then then so based on the matches with the key element, if the key is 4, then the element it will be checked with this, and again next it will be moved to this one, then it will be checked with 4, as like that. So when there are matches, then you will be saying that the key value 4 is found at the position 2, like that you will be searching. So here we will be keep on searching, keep on checking each and every element until we found the searches or matches. Okay, so the here the time complexity of this particular linear search algorithm is, what is time complexity? What is the time complexity of linear search? So we have the time complexity as order of n. Suppose if there are n elements, obviously we are supposed to do the process, repeat the process up to n. Okay, so this is the time complexity. This is an worst case time complexity here. It is not a minimal one, it is the maximum time consuming process. So next we are, in order to reduce the time, okay, in order to reduce the time, we moved another concept called binary search, right? So binary search here, we are, instead of searching each and every element like this, so we have divided the array into, or the list of elements into two halves. Okay, so one is what's that, left half, another one is the right half, then we have a mid element. Then the key will be compared with the mid element first. Okay, if it matches the mid element, then what we will conclude, the element is found at the position where the mid element is present. Okay, suppose if the key value is, then we will be checking If this particular condition is not satisfied, then obviously we will moving to the condition whether key is less than the mid element. Okay, so if this particular condition is getting true, then we will be moving to search an element towards the left, right from index 0 to the element before the mid element, that is mid minus 1 position. Right from position 0 to mid element we will be searching. So likewise, if suppose if the key is greater than the mid element, if the key is greater than the mid element, obviously our searching will be at the right side. If this condition is satisfied, then we will be moving to the right of the mid element. Then this is the position where the mid element, this is the next position of the mid element. So it is the position represented as m plus 1 to R. This is the last element. So only within these list only we will be searching it. So in this way, the binary search technique, obviously one important problem in this binary search is this arrangement of the element should be in order. Okay, that means this binary search technique will be applicable for ordered list of elements, only for ordered list of elements. So before implementing the concept of binary search, we are supposed to sort the element either in ascending or descending as per the demand or the need. Then only we can proceed with the what binary search techniques. So here the time complexity of this binary search technique is order of what of order of log n. Okay, order of log n. So comparing to this order of n, this order of log n is little okay. This is little okay, but this is also not an efficient one. So that in order to minimize the time complexity further to a constant time like a big O of 1, we are moving to the technique called hashing. Okay, so we can achieve this particular time complexity of order of n, which is an efficient one, constant time complexity, with the help of a technique called hashing. Okay, so this is the history of hashing, why we are using hashing technique. So in order to overcome the problem of time complexity, we are moving into the concept of hashing technique. Okay, so how the hashing technique processes, how it searches the element and all, we will be seeing now. Okay, are you all clear about the reason for using hashing technique? Okay. So we are going to obtain the time complexity as order of 1 instead of order of n or order of log n. Okay. So that's why we are using the hashing techniques. Okay. Then let us come to this hashing techniques. Let us come to this hashing technique. Okay. So let us take an example array or list of elements or keys as like that. I'm writing it as key 8, 3, 13, 6, 4, 10, 50. Okay, you consider these are the list of elements. Okay, then in terms of your hashing, what we will be doing is we will be placing the element at its respective index as same as that of its value. Okay, for example, we are calling this as the key space. You consider it as a key space. Okay, right, you consider it as a key space. So in this key space, what we are doing is we are specifying the elements 8, 3, 13, then 6, 4, 10, 50 as it is. Then we have a another one structure called hash table. Okay, so this particular hash table would be the structure will be like this. Okay, the table structure will be like this. So this table contains index 0, index 1, index 2, index 3, index 4, so index 5. So likewise the index will go. Okay, so likewise the index will go up to the maximum number of elements what we are having. Then as per the concept of normal hashing techniques, we will be placing the elements at its respective value itself. So for example, I'm writing one thing, 1 minute, 5, then I will minimize it. 5, then I'm extending 6, then it is position 7, then one more thing, position 8. Okay, position 8. Likewise, the index will go. Okay, so while we are mapping with this index with its respective value, see here the key value is 8. So in the normal hashing technique, the 8 is mapped with the position of its respective index where 8 presents. 8 is mapped at the position where 8 presents. Then if it is 3, obviously this 3 will be placed at the position where the index is 3. Okay, now 3 will be placed here, 8 will be placed here. Similarly 13, we don't have 13 here. So for 13, there must be an index called, it will go up to 13. Okay, or I can draw here. So it will go up to 13 like this. Okay, 9, 10, 11, 12, then 13. Index 13. Is it visible clearly? Okay. So again it will go up to 13 like this. Again what will happen? This 13, this is 8, then 9, 10, 11, 12, 13 and 14. So what will happen now? The element 13 will be placed at the location where we have the index 13. Okay, now 13 will be placed here. Are you all able to view this clearly? So in such a manner, the elements are placed or moved to the respective location of their value as an index. 6 means at the index 6, the elements will be stored. Similarly, 4 means at the index 4, the element 4 will be placed. So suppose if we are having element 50, if so, what would be the risk here? What would be the risk here? So if there are 50, an element 50, there the hash table should be extended up to the index 50. Then only we are able to place the key at location 50. If so, you are able to understand the disadvantage of this structure. Are you all able to understand the disadvantage? What's the disadvantage over here? There are lot of memory spaces getting wasted. Are you all able to see this? So these are the memory spaces, these are free spaces, free spaces, free spaces. So likewise, if it is 50, then beyond this value 10, then beyond this value 13 up to 50, the memory space will be empty. Okay, so the memory space is getting what's that, wasted. Okay, so that we are moving to the technique where we will be following a hash function. Okay, I will write the function now. We will be using a hash function. So that hash function is denoted as h of x equal to x modulo division size. Okay, so why we are using this particular technique, hashing function? In order to overcome the drawback of memory wastage. What is the drawback here? What is the drawback here? Wastage of memory, right? Wastage of memory is the drawback, right? So in order to overcome that, we are moving to the hash function. Okay, that function is denoted as h of x, where h of x equal to x modulo division size. Okay, so suppose let us take the same thing with 8, 3, 13, then 6, 4 and 10. Okay, you imagine that we are having an element at the or the key with the in the key space is as like this. Okay, this is the key space where the elements are stored, and another one is our hash table. Okay, so here totally how many elements we are having? 1, 2, 3, 4, 5, 6 elements. So we can have for example I'm creating the hash table with an index as like this, maybe index 0, index 1, index 2, index 3, index 4, 5, 6, 7, 8, and I can have up to 9. So here I can say that the size of the size here, the formula has size, no? Size represents the size of the hash table. So what's the size of the hash table? Right from 0 to 9. Totally the size is what? 10, right? Suppose if I want to place an element, for example, I want to place an element 8. Okay, suppose if I want to place an element 8, what I'm supposed to do is I need to consider key as 8. Okay, then key as 8 means this is an x. Okay, then I need to compute the hash function as h of x equal to, or h of 8 equal to 8 modulo division 10. So what is the value of 8 modulo division 10? Obviously 8. Obviously it is 8. Okay, wow. So the element 8 will be placed at the location where we have an index 8. Where we have an index 8, the element 8 will be placed. Element 8 will be placed in this location. Are you all clear about this? Similarly, we can place 3. So 3 modulo division 10. 3 modulo division 10 is obviously 3. So you can move 3 to the location where the index is 3. Okay. So next we are coming to the value 13. So now the key is 13. Then 13 modulo division 10 is obviously 3. Okay. So already at position 3 we are having another one element, that is 3. So that what happens now? So now we are trying to fetch the same position for the two elements. Already 3 is there. So this is the area where collision occurs. So collision means what? Trying to use the same place by two or more elements. So now the collision occurs. So we are suffering by the issue called collision. Okay, so you can make note of this issue as a collision. Please make note of it. If you are really taking notes, you please write it as a collision. Okay, collision. So now you leave it as it is. Okay, I will tell you how to overcome this collision and all. Okay, well, so next, this is 6. Next, we are coming to the key 6. So what is the position of 6? Obviously 6 modulo division 10. You will be storing value number 6 at the index 6. Similarly 10 modulo division 10 is obviously 1, right? So 10 modulo division 10, obviously 0. So 10 will be placed at the index. What's that? 10. Sorry, index 0. Clear? Are you all clear about this concept of storing it? Okay. So what is the issue we have faced in this methodology? What is the issue we faced in this method? Collision. Okay, we faced the problem of collision, right? So now we need to overcome the collision, right? Now we need to overcome the collision. So how we are able to overcome the collision? That is what the next content. Okay, so any idea about collision overcoming techniques? Huh? Next position. So what is the name of that particular technique? Okay, see, we are coming to the concept of collision resolution. Okay, collision overcoming techniques we are learning now. Okay, so in this collision overcoming, collision avoiding techniques. Okay, now we are learning the collision avoiding techniques. Okay, so in data structure we are having two different techniques for avoiding the collision. Okay, so one is open hashing, and another one is closed hashing. Open hashing, another one is what? Closed hashing. Okay, so this open hashing involves one sub technique. So that particular technique is denoted as what? Chaining. This technique is called as the chaining technique. Okay, then closed hashing technique. So there are two subdivisions. So one is linear probing. Okay, linear probing technique. One is linear probing, another one is quadratic probing. Linear probing, another one is quadratic probing. Okay, so these are the two techniques available under the category of closed hashing technique. So there are two main categories. So one is what? One is linear, sorry, open hashing, another one is closed hashing. Okay, so in terms of your open hashing, we will be having a method called chaining. In terms of closed hashing, we are having two methods called linear probing as well as the quadratic probing. Okay, so let us come to the part of what? Chaining. Okay, so chaining, as per the name, as the name indicates, that what we will be doing is, so I'm writing the same key space, same key space with the values 8, 30, 3, 13, 6, 4 and 10. Similarly, the hash table, okay, so this is index 0, 1, 2, 3, 4. So likewise the index will go up to its size. Okay, so what is the hash function we are following here? What's the hash function we are following here? We follow the function h of x equal to x modulo division 10. X modulo division, sorry, it is not 10 actually, x modulo division size. So in this particular example, we have taken the size as 10, so that I am replacing it by x modulo division 10. Okay, so as usual, we are trying to move the elements, place the elements. So x modulo division, 8 modulo division, 10 would be 8. So 8 will be placed at the location where the index is 8. Okay. Similarly, 3 will be placed at the location. So one more important thing you please remember, here we are not placing the element at its respective location. So instead, what we are doing is we are creating some form called chaining. Okay, so while you are coming to this particular element 3 modulo division 10 is 3. So at the index 3 we are creating another one node where we will be placing the element 3. Please look at the board. So at the index 3 we are creating a chain, so that chain will accommodate the value 3. Okay ba? The next one, again next we are coming to 13 modulo division 10. It is also obviously returning position 3, remainder as 3, right? So this particular value causes the collision here, so that what we are doing, we are creating another one block as a chain of the previous one, and here we are placing 13. Okay, so this method is called as the chaining method. Are you all clear about the statement? What is chaining? So chaining means instead of placing the element in the hash table, we are creating a chain over there. Okay, so these are the chain. Okay, these are the chain we have created. Are you all clear about this concept of chaining? So in order to overcome the collision, we are adopting the open hashing technique. So chaining is one of the method belongs to that open hashing. Are you all clear about this? The next one, we are moving to the next method. So what is the next method? What's the next method of hashing? Collision prevention or collision avoiding technique? What is the next one? The next one is what? We are using the linear probing method. Okay, so what is the concept of linear probing? Now we will move to the concept of linear probing. So linear probing method, we follow the procedure of identifying the next free position. Okay, so that method is called as the linear probing method. Okay, so now we are moving to the next method called what? Closed hashing. Okay, closed hashing. So closed hashing, we have two techniques. So one is linear probing, another one is what? Linear probing. Another method is what? Quadratic probing. Linear, another one is quadratic probing. Okay, so now we are seeing an example for linear probing. So same key space I am taking here. Okay, so here it can be of elements like same 8, 3, 13, then I'm choosing 6, 4, then 10. Then I am drawing the hash table here with its size is 10. Okay, hash table and its size is 10. So index 0, 1, 2, 3, 4, 5, 6, 7, 8 and index 9. So I am referring the size of this hash table as 10. Size equal to 10. This is a hash table. Okay. So now we are following the same, don't sleep. We are following the here we are following the same hash function h of x equal to x modulo division 10. Okay, same hash function we will be following, but we will identify the position as the next element if not satisfied. Again we are moving 8 modulo division. Sorry, here the hash function will be the same. Hash function will be the same. Okay, but additionally we will be computing one more hash function, that is initially h of x equal to x modulo division 10. Okay, this is the first formula. Then we are computing h dash of x. So how we are going to compute this h dash of x is h dash of x equal to h of x plus f of I, okay, modulo division 10, okay, where f of I equal to I, and I can be starts from 1 0 1 2 3, likewise it will go. Okay, so this is the formula. So let us take this particular 8 means obviously 8 can be placed at position 8, there will not be any collision. 3 means 3 can be placed at the position 3. Okay, so there will not be any collision. But while you are coming to the value 13, we will be facing the collision, right? So what is the reason now? So why we are getting the collision? We are having already element 3 at that place. So that now I am calculating h dash of 13 equal to h of 13 plus f of I. Initially I am taking I value as 0. Initially it is 0. Okay, so f of 0. Okay, f of I equal to I is the formula. Okay, so that you are supposed to place the I value where we are referring f of 0. Okay, so f of 0, then modulo division 10. So what is the result now? H of x equal to 3. 3 plus f of 0 is 0, then you are getting 3 modulo division 10. Again it is giving the space as 3. So here we are facing the problem of collision. Again we are facing the problem of collision. So how we are overcome this collision means by again iterating with another I. So now I becomes 1. Okay, initially it is 0, next we are taking I as 1. So again we are computing the hash function h dash of 13 is equal to what is this, h of 13 plus f of 1. Instead of 0 we are placing 1 here, f of 1 modulo division 10. So h of 13 is obviously 3 plus f of 1 is what, as per the formula it is I. So 1 is I equal to 1 means again it will be 1 here, then modulo division 10. So what is this modulo division 10 says? 4 modulo division 10. Obviously it will return the value as 4. Okay, so now based on this index value you have calculated, we are placing the element 13 at an index 4. Okay, so that is what the next position of the previous element. Okay, so initially we are checking at this position where we face the problem of collision. So we move to the next position. How we are identifying the next position is not just like that, by applying the iteration of the hash functions again and again. Suppose if this position also have some element, for example here I am including one more element. Please make note of it. Suppose I am including one more element like this. For example, okay, for example I am taking 23, number 23. So where the 23 will be placed now? So now 13 was placed at the location position 4, right? So here 13 was placed at the position 4. So 13 was placed in this position due to the collision. Next we are getting another element 23. Then where will you place 23? Again you need to follow. So obviously h dash of 13 with I equal to 0 will be position 3. Then similarly I equal to position what's that, 1 also will return the position value as what, I1 will return the position value as 4. Okay, so since at the position value 4 we are already having an element, so this is collision and this position also collision. And again what we are doing, we are incrementing I to 2. Now we are applying h dash of 23 is equal to what's that, h of 23 plus f of I, okay, plus f of I, then modulo division 10. So what is the value now? H dash of 23 equal to 3. F of I equal to what? F of I equal to I. That means I value is now 2. So that 2, then modulo division 10. So 5 modulo division 10. So 5 modulo division 10 will be the value 5. So now the new position of the element is position 5. So that here only you are supposed to place the element 23. Are you all able to understand why we are placing, how we are identifying the next question? Are you all clear about these statements? So this is the case of, or this is the concept of linear probing. Are you all clear about this? Yes or no? Yes, right? So next one, once again I repeat, we are having closed techniques, linear probing, and another one is quadratic probing. Linear probing, we are applying the formula. Please remember this formula to identify the position of the element. Okay, we are identifying the position of the element by using this formula. Then we are moving to quadratic probing. So quadratic probing is almost the same as like our linear probing. There the formula for calculating the index will have, instead of f of I, we will be having f of I square. Okay, so the next one is quadratic probing. So the next one is quadratic probing. Okay. So quadratic probing, this is same as that of your linear probing, but the difference here is in the formula of calculating the index. So here we will be using the formula h of x equal to, as it is x modulo division 10, then we will be using h dash of x. H dash of x equal to, the formula would be h of x plus f of I square. Instead of I, here we will be using a formula called I, formulas such as I square. Okay, we will be using I square. So now you apply the collision keys with this formula, then you are all able to identify. Why we are moving to quadratic probing? What's the reason? Please, can anyone say why we are moving to quadratic probing instead of linear probing? Any reason? Any idea? See, look at this. In case of your linear probing, we are facing a problem called clustering. So here the drawback of this linear probing is problem of what? Clustering. Okay. So what do you mean by clustering? Clustering means accumulation of many elements in a within a small spaces. Okay, see here we have accumulated many elements within a small space. Obviously all these three elements, 13, the what's this 3, 13 and 23, all are occupying the all must have at the position or index 3, but due to the concept of that linear probing, we have moved to next elements, next positions. So but there are this is looks like a cluster. So in order to overcome this clustering, in order to overcome the accumulation of elements at a same location, we are moving to the concept of quadratic probing. Okay, so that is the reason of moving to quadratic probing. So quadratic probing, instead of I, we are following the method of I square. Okay, so the same way you can calculate. Suppose if the key space is, if the key is 23, then how will you proceed with this 23? When I equal to 0, we will be getting position as what? 3, I think. Let me calculate here. H of 23 equal to, what will happen? H dash of 23 equal to h of 23. What is the value of h of 23? 3 plus f of 0. Obviously it is 0. So you will be getting a position 3. So position 3 already having an element, so it is collision. Then the next one is I equal to what? 1. So when I becomes 1, what will happen? H dash of 23, again it will becomes a value as what? 3 plus f of 1. Okay, so here I forget to mention where, sorry, 1 minute, please do the correction. Please do the correction. It is f of I only. Here the representation is f of I only, where f of I equal to I square. This is the correct way of representing this function f of I. Please correct it. If you are making note of it, please correct it. Here the same f of I, but in f of I is I square. So in previous method where we used in linear probing, f of I equal to simply I. But here in quadratic probing, f of I would be I square. Okay, f of I would be I square. So that 1 square, again f of I equal to 3 plus 1 square equal to 3 plus 1 equal to 4. Again here we are facing the problem of collision. Okay, again we are facing the problem of collision. So once again moving to the next iteration of I. So I now becomes I equal to 2. So when I becomes 2, again h dash of 23 would be what? 23 equal to 3 plus f of I is now 2. Okay, f of 2 equal to 3 plus 2 square equal to what? 3 plus 4 equal to 7. So now we found the position 7. So in our list, we don't have the element at position 7. So obviously this particular element, what's this, 23 will be placed at the position 7. Okay, are you all clear about this concept, how we are placing the element? Instead of clustering the element at one particular location, we are identifying the different location. By the way, we are overcoming the problem of clustering occur in linear probing. Oh, okay, so that's all about the concept of hashing. Okay, so we have studied about what is hashing. Then how, so here in this method, we are able to obtain the time complexity as big of 1. Okay, so this method is what, very efficient method comparing to the previous methods. Okay, so by the way, here the index 7, the 23 is placed. So that's all about the hashing techniques. Are you all clear about this concept? Okay, thank you.